Hi, my name is Marcelo, and I'm going to present an MDS timbre space for musical instruments generated by physical modeling synthesis, which is work that I did in collaboration with Josh Mitchell, grad student here in the Department of Music at UC San Diego. So, in order to understand the research question, we need to talk a little about sound morphing and timbre spaces. So, what is morphing? This is obviously just an example, an illustration with image morphing. Usually, we have a source and target images or sounds, and what we are trying to do is to create morphs that are intermediate between the source and the target. And omega here under the images is called the morphing or interpolation factor. When it's at 0, we are at the source. When it's at 1, we are at the target. And intermediate values of omega would place us at intermediate distances, relative distances from the source and the target. And ideally, when omega is 0.5, exactly in the middle, we would be perceptually halfway between source and target, which I believe is the case for the images here, but it's way harder to do when we're morphing musical instrument sounds because musical instrument sound morphing gradually blurs the categorical distinction between the sounds to create perceptually intermediate timbres. So the idea is when you are perceptually in the middle, you would create the sensation of a hybrid musical instrument. So when we think about sound morphing in the context of timbre spaces are sparse, and the musical instruments occupy specific points in what is otherwise void space. So sound morphing can potentially fill the gaps and create continuous timbre spaces. But even more importantly, if we are able to place a morph perceptually halfway between source and target sounds, it would break the categorical perception of musical instrument timbre. So the question behind this research is, where do the morphs appear relative to the original sounds in their underlying timbre space? So thinking about, again, sound morphing in the context of timbre spaces, when we morph musical instrument sounds, the aim is to obtain intermediate timbres, such that the morph should be perceptually intermediate between source and target. Now, in a metric timbre space, M is placed as we see here in the figure, in this line going through the source and target sounds, and now the morphing parameter just sets the relative position of M, how far it is from the source and target sounds. So this is how morphing sounds usually happens. You model S&T with some underlying model that will represent those two sounds. Then you find correspondence between model parameters for the source and target, and you interpolate the parameters respecting the corresponding parameters according to this equation here, where omega, the morphing factor, is what sets how far it is from the source and the target. And then you resynthesize M from the interpolated parameters, the morph. So now, how the model represents sonic information is what determines the perceptual impact of the morph. So, talking about physical modeling synthesis, which basically does sound synthesis using acoustic models. So physical modeling synthesizes sounds from mathematical models of the underlying acoustics of the sound generating phenomenon. So I have examples here, sound textures, for example, it would be stochastic or statistical models. And for musical instruments, the models come from instrumental acoustics. So a very simple example would be the drum, where the model is a two-dimensional membrane that is set into vibration by striking. Now, the model parameters, when it comes to physical modeling, come or are associated with physical properties, such as materials and dimensions of the musical instrument, and also kinetic properties such as intensity and the placement of the strike. So now this would influence the amplitude of vibrations, the modes, and the resulting timbre, which, by the way, is also influenced by the materials, the dimensions, and many other factors. So we are using Pianotech for this specific research, which is a virtual piano synthesizer based on physical modeling. As the name suggests, Pianotech is capable of synthesizing several types of pianos by just adjusting model parameters, such as acoustic grand piano, upright piano, electric piano. And there are even very specific piano models, such as the Grand Steinway Model D, the upright piano, the Rode, and many others. Additionally, Pianotech is capable of emulating other percussive instruments based on similar physical principles, such as plucked strings. I have examples here: the harp, the guitar, the harpsichord, and idiophones, such as the marimba, the vibraphone, the kalimba. And also Pianotech is capable of morphing between those instruments. So I have a quick demo here. I just want to show the interface. So this is what Pianotech looks like. This is what it sounds like. So here we have the Steinway D Classical. You can adjust several parameters, such as the tuning. You can change the temperament. You can change parameters related to voicing, such as the hammer hardness, the hammer noise, the strike point. And you can also change physical parameters. They're called design here, such as related to the soundboard, like so the impedance of the soundboard, the cutoff frequency of the filter associated with the soundboard. There are many other musical and physical parameters, including the pedals and even the condition of the piano. So I can make it or mint condition. All right, so when morphing physical models, we are interpolating the parameters of those physical models, but that does not naturally result in perceptually intermediate morphs because of how those parameters capture different either physical or acoustical or musical properties. So there's a need to perceptually calibrate the interpolation of each one of those. So the hypothesis behind our research here is that perceptually intermediate morphs appear halfway between source and target in their underlying timbre space. So we are going to use the relative position of the morph to indicate the quality of the morphing transformation, basically trying to answer the question, has the interpolation been done satisfactorily? So there are two stages to this research project. I'm presenting only the first stage, original timbre space, and this is future work, the second stage. So the first stage, basically, we create an MDS timbre space using only original musical instrument sounds, so only sounds from different instruments synthesized by Pianotech. Those original musical instruments will serve as reference points for the morphs. So these should remain stationary when we introduce the morphs in the second stage, which is basically to recreate the MDS timbre space with the same original sounds from the first stage plus a few morphs. Now what we want is to visualize where these morphs appear relative to their corresponding source and target sounds. And we want to use the position of the morphs to inform the morphing procedure to help answer that question. Are they done correctly? Have they been properly interpolated? So now, this is the results of a pilot study that we did. So these are considered preliminary results. The first thing is the sound stimuli that we chose from Pianotech. So the instruments we chose were the church bell, the guitar, the harp, the harpsichord, the kalimba, marimba, piano, steel drum, vibraphone, and the Wurlitzer, which is basically an electric piano, a model, a make and model of electric piano. Now, these are all physical modeling synthesis, sounds synthesized from physical modeling. And so we collected pairwise dissimilarity data, including identical pairs. The identical pairs are used to check data quality. Basically, we exclude participants who rate more than 20% of the identical pairs above 10% of the minimum of the scale. So the identical pairs should be rated identical, 0, right? That's the minimum of the scale. The scale is continuous between identical and very different, and there's a hidden continuous scale between 0 and 10 associated with those two extremes. So we collected data from 29 participants. The listening test for the pilot was online. We used Qualtrics. And what we see here is the dissimilarity ratings for the 29 subjects only for the identical pairs. So what we expect to see here is most subjects rating the identical pairs at 0 or very close to 0. And we have here a few examples. Participant 20 that for most cases rates the identical pairs at 0 but fails sometimes. We have participant 29 that rated one of them at 10 and all the others at 0. So this could be considered as a moment of inattention, right? So use the other end of the scale. And we have 3 problematic participants here, highlighted in red, because these rated more than 20% of the identical pairs at more than 10% of the bottom of the scale. So these will potentially be excluded. But we are looking at the data. We are looking at a histogram of the dissimilarity data. This is going to be visual inspection to help us with the hierarchical clustering analysis, where the goal is to compare the participant ratings and identify people who did not understand the task, who has a very different dissimilarity matrix from the others. So basically, we perform a pairwise correlation between the dissimilarity matrix for all of the participants, and then we perform hierarchical clustering analysis on those correlation matrices using the complete linkage algorithm. So this is what it looks like, those histograms, right? So again, we have all 29 participants here, and what we're looking at is in gray, the histogram of the dissimilarities for the different pairs. And then here we have in red for the identical pairs when they didn't respect the 20% threshold, or in blue when they did, right? So for some participants here, the histogram, this is perfect. This participant rated all identical pairs at 0. And then here are the others. So what we can see is, first of all, these 3, they still obviously didn't follow the procedure for the identical pairs. And we can also see the histogram of their dissimilarities. Now, I want to draw your attention to participant 29. When we saw participant 29 at first, that 10 seemed like a moment of inattention. But here, what we have is participant 29 actually rated all of the sounds either 0 or 10. So there was that moment of inattention. But this participant didn't understand the task. And we have other participants, such as 19, 20, and 5, who potentially didn't understand the task either. So this is what the dendrogram looks like. What we have here is the square root of 1 minus the pairwise correlation. So this is a distance between the correlation matrices. And here is the index of the subjects. So depending on how far it connects how far up it connects. This is how far this participant's rating is from the other participants. So we can see, for example, that this group, 7, 8, 20, 15, and 29, it connects very, very high up with this other cluster here. Participant 29, which is the one we talked about, is the one that is the farthest away. And there's also here participant 5 that is very far away from the closest cluster. So in the end, we decided to exclude, using the identical pairs, participants 7, 8, and 15, the dendrogram, same participants, plus 20, 29, and 5. And out of an abundance of caution, using just visual inspection of the histogram, we also excluded participant 19. So in the end, we excluded data from these 7 participants, and we're only going to use dissimilarity data from the 22 remaining participants. Now, this is the histogram for those 22 remaining participants. In this case, now the index of the subjects changed, right? Because we excluded participants, and it could be said that this little cluster here is far away from the rest of the participants. But these are considered to be just participants who used a different strategy. So now we want to select the MDS model. So the aim is to choose the number of dimensions of the MDS space. We are using 3-way Smakov for multidimensional scaling, MDS. The constraint here is identity for model selection. We're using ratio, MDS, where the disparities just have a multiplicative constant. And the dimensionality of the space, in order to choose, we're going to do identity from 1 to 7 dimensions and use 3 different criteria. The coefficient of determination, which is a goodness of fit measure. It tells us how much of the variance in the data the model explains. The Aikaki information criterion, AIC, that is a sort of distance measure between the selected, the current model, and some true unknown model. And then we're also looking at the Shepherd diagrams, which is basically a badness of fit measure. It shows us how much residual error still exists between the disparities and the original dissimilarities collected. So for the coefficient of determination, as a function of the number of dimensions that we have here, we can see that it goes up, and it seems to stabilize. I want to draw your attention that for 1 dimension, the coefficient of determination is already 0.99, right? But it keeps going up, and it can be said that at around 3, the variation is very, very small. For the AIC, what we expected to see was high values for low dimensionality, and then a minimum, and then it going back up. And that's not what we see here. For 1 dimension, we see the lowest value. So this might be an indication that the AIC is telling us that 1 dimension is the best representation for that, but I honestly suspect that there might be some mistake in the calculation of the AIC in this case. And then the Shepherd diagram, basically the vertical distance between the distances and the disparities in black here for the different the similarity values gives us an indication of the error. So here we see that this is the Shepherd diagram for 1 dimension, 2 dimensions, 3 dimensions, 4, 5, 6, 7. So when we are at 3 dimensions, it's already quite reduced. So in the end, we decided on a 3D model, and we use 3-way Smakov, also known as Smakov for individual differences. So the ratings of each participant are weighed differently. The constraint we're using is INSCAL, which basically means there is a central model, and the ratings for each participant will just correspond to rotations and expansions or contractions of that central model. We're using also interval MDS for the disparities. And the dimensionality, as I mentioned, is 3D. So this is the final model. This is what it looks like. I also have here an interactive graph. And for future work, we need to collect more data, probably in person rather than online. I need to check the AIC to make sure that 3D is the best model for the data, and interpret the dimensions of the resulting space, correlate with descriptors of timbre, and try to interpret what those dimensions mean, and then go on to do the second stage of the research, adding the morphs. Thank you very much for your attention.